I hope you didn't think we're done with all this bit manipulation business. There are two more really useful concepts that pop up all the way from final exam questions to tech interviews.
Shifting and masking, right?
Think of shifting as you find a position and then you slide either left or slide either right. What position do you start from? Why? The first one, of course, most of the time. The least significant bit, or the LSB, is the first position, the counterpart to the MSB, or the most significant bit that I spoke about in the last lecture. A left shift multiplies the bit I'm looking at by a value of 2, and the right shift performs an integer division by 2. Remember how I said that we use a positional base 2 system? So left shifting is how 1 becomes 2, and 2 becomes 4, 4 becomes 8, and so on. Right shifting is how 16 becomes 8, 8 becomes 4, 4 becomes 2, and 2 becomes 1. There are two variations of shifting, logic shifting and arithmetic shifting. And the only difference here is that in logic shifting, you move the sign bit also along with the other bits, while in arithmetic shifting, you keep the sign bit untouched. So logic for unsigned and arithmetic for signed interpretations.
Example time. If you run out of bits to shift, it will be 0. But for a negative number, it will increase, as you can see here. Meanwhile, masking is a convenient method when we want to change some bits only, but not all of them.
Think of them as wearing masks, right? And you only throw eggs at the ones wearing masks. We use this masking concept to do 4 main things. We use this to check a bit, set a bit, clear a bit, and count the number of differing bits. To check a bit, we usually shift and then apply the mask as an AND operator. So remember, AND times anything will only give you a 1 if both the bits are 1. Otherwise, it's going to be a 0. To find the bit at the 5th position, I'm going to left shift 5 times, and then I'm going to AND it with a 1 and see what I get. To set a bit, we use the OR operation, because OR and anything will only give you a 1 if at least one of them is a 1. So I'm going to take a 1 and I'm going to left shift it 4 times, and then I'm going to apply the OR gate and see what I get. To clear a bit, I'm going to AND it with a 0. So you effectively make it a 0. Remember, you AND anything with a 0 and it's going to be a 0 because you need both things to be 1. I take the mask and I have something known as inverse mask so that I can choose which bits to affect and which bits to not affect. So the inverse mask is basically what was there in the original position. You find the number of bits to change one number to another. So you want to convert A to B. You want to see if changes happened that was unexpected in some sort of communication or transmission. So you use the XOR gate. Remember, this looks at a difference or the difference in levels, or it counts the odd number of ones. So if there's any sort of funny business going on in the number of ones, it's going to pick that apart. So if you XOR the same number, you get a 0. But if you XOR a 1 and a 0 and a 0 and a 1, you are going to get a 1, which means that there is a difference.
In languages such as Python, which we'll be using in this course, only signed integers are natively supported. This means that everything implicitly has a sign, and you don't have to worry, except if your memory is running out. Languages give different granular control over how many bytes to allocate for your data.